Hey guys, welcome back. We're starting our last chapter over bivariate data. We will be testing over bivariate data whatever day you will be in class next week. So whether that's Monday, Tuesday, Thursday, or Friday, you'll be taking the test in class with me. So let's go ahead and get right into it. This is my favorite unit, I would say so. At least one of my favorite units, I don't know. And probably one of my favorite chapters in there. I really like bivariate data, how the correlation coefficient is calculated. I find that fascinating, how it's all based on z-scores, how that's the slope of the standardized stat plot, and then how we get to the real world units from there. And then re-expressing the data is pretty stinking cool as well. So today we're going to look at the fuel economy versus weight for vehicles. So as you would expect, as we increase the weight of vehicles, their fuel economy is going to decrease. But the problem we have here is that the model, just like the dive heart rates with the penguins, they're not going to be linear. So if we look over here, when we always graph the residuals, you'll notice there's some gaps here, which shows that we have a general trend of some curvature going on with our model. And as we can see there, we're graphing out with a line of best fit, what's really actually looks something along the lines of y is equal to the square root of, or y is equal to 1 over x, so the reciprocal of it, right? So we've got some asymptotic behavior. The fuel economy, fuel efficiency, of course, can never be less than 0. We can't have a negative fuel efficiency, and it's only going to get so good as well. So there's kind of asymptotic behavior going on there. Let me back up here. The r squared here gives us a coefficient of determination, tells us that 81.6% of the variation in fuel efficiency can be accounted for by the model with the weight, which is good. But if we re-express this data to make it linear, we could actually account for more variation, which would be very nice if we were able to re-express it. So the coefficient of determination is based on the correlation squared, right? But correlation is only the appropriate measurement of the strength of the association if it's a linear association. And as we just said, this was not linear, and so it would actually be even better if we could straighten it out first. We'd have a higher correlation, which is at that point, if we were able to make it linear, and we would have an even better, we would be able to remove even more variation in the fuel efficiency based on our re-expressed values. So let's look at the Hummer H2. So the Hummer H2 is a very, very heavy vehicle at 6,400 pounds, way heavier than anything that we had in our within our domain or within our actual data here. So we are definitely extrapolating. But if we use this model, and again, the reason it's breaking down is because the model is based on this data, which the data kind of tends to suggest like it's going to be, you know, something like that. So it will approach 0, but you can't have anything less than 0, right? And with the Hummer, it would actually give us a fuel economy of -5 miles per gallon, which is not possible to have negative fuel economy. So yeah, that's not going to work. Clearly, there's something that's breaking down here. Well, our problem is the way that we actually do miles per gallon. So it's actually backwards, I believe, than how they do it in the UK. So let's look at that in a second. So miles per gallon is basically how many miles can you go on 1 gallon of gas. Makes perfect sense to me. But in the rest of the world, or I guess in other places in the world, I'm not sure how everyone else does it. But I wouldn't be surprised if America's backwards, because, you know, that's how we roll. On 1 gallon of gas, I'm just kidding. How far do you roll in 1 gallon of gas? So the rest of the world does, I believe, something along the lines of how many gallons does it take to go 1 mile, or not just 1 mile, but how many gallons does it take in order to go 100 miles, or probably they would use kilos per liter or something like that. Okay, so if we switch it, kind of doing a reciprocal, instead of doing miles per gallon, we're doing gallons per miles. You see how the pictures kind of help you see what we're doing. When we re-express that in fuel consumption for gallons per 100 miles, we'll get something that is now a positive association. So as we increase in the weight, it takes more gallons of gas to go 100 miles, as you would expect, right? And then also here, you can see our scatter plot that we graphed. There's still, you know, there's still some pattern here going on here. Their data is actually still going to be curved, except now it's kind of curved this way instead of being curved that way. But the real reason why it's better to re-express it is now there's no limit. We can just keep increasing it as we go. And so we'll get a value that actually kind of makes sense here. So as we increase our weight up to 6,400 pounds, we would get about 9.7 gallons per 100 miles. So that's going to take a lot of gas compared to the others, which all take less than 7 or 6.5 gallons per 100 miles. And then if we take the reciprocal of that, so 100 miles and 9.7 here would give us about what we were used to, about 10.3 miles per gallon, which is how we would estimate that, or we would state that in America, right? And if I looked it up, I think the Hummer H2 does get, they estimated 10 miles per gallon in the city and 13 miles per gallon on the highway. So our estimate and our model was actually not too far off, even though we would expect, if we're following the curvature here, the data actually looks like it is curving this way, so our value should actually be less than that. But anyway, that's why, you know, linear model curve data, they don't work. And that's especially when you're extrapolating like we are here. You're going to run into a lot of problems. So why do we do the reciprocal? Well, when we have y is equal to 1 over x, stuff that looks like this, if we take the reciprocal of that, which would be like basically 1 over y, so we're taking the reciprocal of the response variable, well, 1 over y is equal to 1 over x is really the same thing as y is equal to x, which is, of course, linear. So that's why it turned from a reciprocal to something linear, which is kind of cool. And a lot of times you can think about the functions and how you could re-express or change the x or the y variable. Typically, we re-express the response variable in order to make them linear, and it kind of works. It's pretty nice. So one of our goals for re-expressing data is to make distributions more symmetric. So we are talking about distributions, which would be univariate data, like the histogram, instead of bivariate data with scatter plots. So if we look at the top 500 companies and we graph out their assets, which is the total amount, cash value of their property, whether that be vehicles or real estate or whatever's going on there. And then we're graphing out the assets in 100,000. So this 40,000 times 100,000 would be $4 billion. So there are only 2 companies, it looks like, or yeah, probably about 2 companies that had a total net worth of more than $4 billion. There were several large, between 2 and 4 billion, but most of them are going to be less than $1 million or around $1 million for their total net worth. The small businesses, right? Even the top 500 companies, there are very few that are really, really, really large. All right, so this data is clearly going to be heavily skewed to the right. And anytime we have data that's heavily skewed to the right, we can re-express it by using a logarithm. And the reason a logarithm works is because a log is basically asking a 10 to what power will give us that value. So 10 to the first power, or the log of 1, base 10, would be 10. Log of 2 would be 100. So we're going from 10 to 100. It's increasing pretty quickly. And then log of 3 would be 10 to the third power, which is 1,000. So we went from 10 to 100 to 1,000 to log 4, which would be 10,000. And then you just keep going, right? So 100,000, a million. So if we do the log of 4, that's going to be 10 to the fourth power, which would be 1,000, right? Log of 3 is 100. Log of 2 would be that would be 100. I'm sorry, I got off by 1. But anyway, the log of 1 is just 10. So as we get these really, really heavily skewed values, they're going to be brought closer together, and the values that are smaller are going to be spread out as well. And so what's amazing is by taking the log of assets, we now have something that's unimodal and symmetric, like a bell curve. And so it's fascinating. Another thing is a natural log is just the base of E, which is, I think, 2.81. You can put it in the calculator. It's stored in there, but just like pi. Anyway, so E, the natural log is just base E. So it works in exactly the same way. The numbers are going to be different, but it will has the same effect of re-expressing the data as a logarithm does a natural log. So why do we use the logarithm? So I've graphed here the natural log of x, and you'll notice that as the x values increase, the y values are increasing very, very slightly because it's using an exponential rule. So y is equal to log of base b of x, so b to what power of y essentially is equal to whatever value of x that we were interested in. So it's basically using exponents to bring things back together. So our second goal is to make distributions more comparable. So if all of our data here is skewed to the right, so these are again the assets for different companies and different market sectors, and all of these distributions are going to be skewed to the right because there's going to be very large companies apparently in high tech and finance where our big outliers with the 4 billion were coming in. And so if we take the logarithm of all these distributions, you'll notice that now they're much easier for us to kind of zoom in and see the minute differences here. So these far outliers are now just going to be our right bounds, and there's not even any outliers. And then all this, see how all the data is kind of squashed and crunched up on the left towards the low end? All that's now going to be spread out, just like we saw whenever we re-expressed it in one variable. The same thing is happening, but it's happening across all these box plots and their summaries, their 5-number summaries here, which allows us to more easily compare. So you could see the most consistent one we would say would be transportation, because it had the smallest interquartile range. The smallest overall range, it looks like, was either transportation or retail, going from the max to the min. The only outliers we had were on the low end with these really small finance companies and stuff like that. So we couldn't get that information over here because everything is skewed to the right. But here we can see, using the logarithm, what's really going on. And there are still some that are skewed, which would mean they were majorly skewed, which would be energy companies. All right, so our next goal is to make scatterplots more nearly linear. So if you notice, we have the same problem here. All the data is towards the low end of the assets, and so it's going to make it curved, and it's not going to work out too well. But if we take the logarithm of the assets, now it's going to spread it out. All the stuff that was crunched up on the bottom is going to be is going to be spread out just in general. And then all the stuff that's further up on the top is going to be brought down, and so that's going to make it really look pretty linear. It's not a very strong association, but it's clearly linear at this point. All right, then the other one is to make the spread more even. So as we get across our model here, it is crunched up, but you'll notice over here that the spread is much more even across the board at any point of our domain. And on this one, they actually did the log of assets and the log of sales. So we'll talk about the ladder of powers and the attack of the logs tomorrow. Or whatever day you're watching this. So we'll talk about that. So sometimes you can actually take the logarithm both sides, and it really straightened it out in that case. All right, so a company manufactures polypropylene rope in 6 different sizes or diameters. To assess the strength of the ropes, they test 2 samples of each size to see how much force in kilos the ropes will withhold without breaking. The table below shows the results for these tests. We want to create a model for predicting the breaking strength from the diameter of the rope. Create a scatter plot of the data, and what do you notice? Does it look linear or slightly curved? So remember, there are actually 2 of each diameter. There's 2 strengths because there were 2 ropes that they tested. So we're going to go into stat, edit, and then for list 1, I'm going to put 2 of them with a diameter 4. One of them had a breaking strength of 60 kilos and the other one 76. Okay, so then we had 2 7s, 2 10s, 2 12s. You can see I put the data in. Okay, then we're going to graph a scatter plot. So go to second y equals. I'm going to turn the plots off, which is the 4th option, and then go back into there. And I'm going to turn on the first plot, do a scatter plot from list 1 to list 2. That's my X and my Y list, and then go to zoom and 9 to graph that out. Okay, so I shouldn't have the model on there yet. That's a bit of spoilers. So anyway, that is our scatter plot, and when we graph it out, it looks like this. Notice that the data is going to be pieced together because there were 2 with the same domain for each one of those, and so that's why it's stacked that way. All right, does it look linear or slightly curved? I would say it looks slightly curved. It's not too bad, but it is slightly curved. All right, so calculate the linear regression for the model. So to do that, we want to go to calculate. Stat, arrow over to calculate linear regression is the 4th option from list 1 to list 2. I'm going to go ahead and store the regression equation because we're going to use it for a prediction. So I go to variables, y variables, function, y1, and then hit calculate. So there's our linear regression, which I just stored over here. Calculate the correlation coefficient. So the correlation is going to be 0.979, which would suggest that it was a strong correlation. But again, if we look here, it was actually curved. So that's not an appropriate measurement of the strength of the association because it was curved. But nonetheless, we have a high coefficient of determination, so that will allow us to remove a lot of the variation in the response variable by using the y. All right, so we got the correlation and the coefficient determination, so we're good. Draw a quick sketch of the residuals. So every time we calculate a linear regression, it always stores the residuals in the second list, and it'll be on the very bottom here. So it'll always do that for you. So let's go ahead and graph the residuals. So go to second y equals for the stat plot. And now I'm going to go from list 1 to the residuals, which I find that in the list menu. So second stat, which is the list in blue there, arrow to the bottom, get the residuals, and then hit zoom 9 to graph that out. Okay, again, it graphed the model. That's because it all automatically turns it on for you. So anyway, go back to graph. That's going to be our residual plot. And you can see clearly from the residual plot that we do have some gaps here. So we do have curvature in the model itself, which doesn't show up as easily as you can see here in the scatter plot, as we see in the scatter plot of the residuals. Okay, so we have the rope's diameter and its strength here. So again, you always graph the scatter plot of the residuals to check to make sure that there's no pattern that will let us know that it is actually indeed linear. Company is thinking of introducing a new rope with a 25mm diameter. How strong would you expect it to be using the model in part B? So from our linear regression, we have our slope, our A, and our B, our y-intercept. We're predicting the strength, so we do strength hat is equal to A times the diameter, which is our explanatory variable. We put in the values of A and B from our linear regression, and we want to evaluate it at 25. So if we're doing this in the calculator, since I've already run the linear regression, you can go to... I don't know why that always happens. Anyway, variables, y variables, function, y1. Then I'm going to evaluate this at 25, and that will give me the predicted strength. So we would have a predicted breaking strength of 1106 if we wanted to round kilos. So 1106 kilograms. All right, if the y value seems to follow an exponential pattern similar to y is equal to x squared, then what would we do to the y list in order to straighten it out? So for the y list, in order to get rid of the square, we would do the square root. So let's take the square root of our response variable, which is the strength. And if we think about it, if we measure diameter, well, as the diameter of a circle, right, is increasing, we're actually increasing the area by a factor of a square, essentially, because we're taking like a radius squared times pi, right? Pi r squared is how we get the area. So we're going from 1 dimension to 2 dimensions because we're really, as we increase the area would be proportional with the strength, not the radius or the diameter. So what we want to do is we actually want to take the square root of the strength. So I'm going to go into stat and then hit edit. And for the list 3, I'm going to define this as a square root, which is second x squared, the square root of list 2. And then hit enter, and that'll do list 3 that way. And then I'm going to go ahead and graph a scatter plot, but this time the scatter plot I'm going to do is going to be using list 3. So list 1 and list 3. Okay, and then I'm going to hit zoom 9, and we're going to see that's actually much straighter. And then I'm going to run a linear regression to see what happened here. So linear regression, and I'm going to do it from list 1 to list 3. And then I'm going to store the regression equation again. I'm going to store this one as y2. That way I'll have both of them in case I want to go back. Okay, cool. So notice now what happened to our correlation coefficient. So here's the original model, which had some curvature in it. Then after we took the square root of the strength, it straightened it out, which is really cool. Between the original correlation coefficient and the new one, it went up. So it's almost 1. It's almost a perfect association in this case, or perfect correlation, because it's almost positive 1. And instead of only being able to account for 95.85 or 95.86% of the variation, now we can account for 99.63% of the variation in the strength can be explained or accounted for by the model with the rope's diameter, which is kind of cool. So it's very, very predictable. In other words, very, very stable. All right, then. Yeah, so what is the correlation of the re-expressed data? We got that right there. Draw a quick sketch of the residual plot for the re-expressed data. So notice there's no pattern in there anymore. And also you can't use the residual plot in order to see like how accurate the prediction is, because what happens, these are actually really close to the line, but they always zoom in the scatter plot. Hopefully that makes sense. So like here it looks like 1 point, but it's actually 2 points. They're just so close together you can't even tell. Okay, and so the parts that are the furthest apart, those are going to be, of course, the largest that they do, because when we do zoom stat, it zooms in as best it can to fit all the data in one window, whatever that window is. So we can't, if we want to know our average prediction error, you would take the standard deviation of the error, or work backwards from the variation, subtract the the amount of the percent of the proportion of variation that was able to be accounted for by the model, which is the R squared there, our coefficient determination. Anyway, stuff that we've already gotten into. So much better model when we re-expressed it there. All right, companies think of introducing new rope 25 millimeters. How strong would you expect to be using our new model in part F? So now notice it's a re-expressed strength. The predicted strength, square root of the strength, is going to be equal to our new A and our new B. So to do that, I've already done that, which is exactly the same thing I have here. Okay, so basically I'm plugging in the values here. I'm going to evaluate my equation, which is going to be y2. If you remember, we saved it as y2. So I'm going to evaluate that. I'm going to go to variables, y variables, function y2. I'm going to evaluate that at 25. But, okay, so this is 36.97. That's going to be the square root of the strength. So the square root of the predicted strength is 36.97, right? So if that's what the square root of the predicted strength is, I want just the normal strength in kilos, not square root of a kilo. That's a weird unit. So how do you undo a square root? Well, we're going to have to re-square it when we're done. So take your value, square it, and that'll give us our actual predicted strength using our new model, which is much more appropriate because it's been re-expressed to make it straight in this case. All right, so what's the difference between the two predictions? So our last prediction with the correct model and the one with the inappropriate model would give us a difference of 261 pounds, and we would trust this one much more because of the residual plot had no pattern and it clearly was re-expressed and is now linear. Okay, cool. So for each model below, predict y when x is equal to 2. So we want to make sure that we know how to evaluate these models. This is a re-expression of squaring the response variable because it's squared here. So whenever we evaluate these for 2, you can put it in the calculator. So we're going to do 0.8 times 2, and then we're going to add 12 or 1.2 to that. Okay, now that's going to be 2.8. So if I rewrite this over here, essentially what I'm going to have is the predicted y hat squared is equal to, was that 2.8? Yeah, 2.8. Okay, well that's not what I want. I don't want y hat squared. I want just y hat. So I need to take the square root of both sides. So the square root of 2.8. So that caret 0.5, which is the 1/2 power. It's the square root, is going to give me a new value. So the y, the predicted y, is going to be equal to 1.67. Okay, same thing here. This is actually a reciprocal square root. I think we actually usually do the opposite reciprocal square root. But anyway, so the reciprocal square root, so same thing, exactly the same thing we got there. But now the way that we undo this is with taking the negative square. So the negative power is going to do the reciprocal, which is going to move it back to the top, and then squaring it's going to get rid of the square root on the bottom. So let me see if I can do that real quick. So I'm going to take the same value I had before because the rest of the thing is exactly the same. So 2.8, and then I'm going to take it to the negative, so caret -2 power. And that's going to give me a different value of 0.127. Okay. All right. So the rest of the problems I want you to try on your own. You've got the answers in the back of the book. They're all odd. So go ahead and go through those. And if you have any questions, I'm not doing the live office hours because we have I've got classes that I'm teaching throughout the day now. But if you do have any questions, please reach out through Google Classroom. If you want a quicker response, maybe try Remind because it goes straight to my phone and I can respond to you no matter where I'm at. So anyway, I'll see you guys later. Have a good day.